Mathematics, at its core, is a quest for truth. It's a language that describes the universe. We use it to predict the weather, design bridges, and understand the very fabric of reality. But what happens when math leads us to conclusions that seem impossible? What happens when the pursuit of logic leads to paradox? These mind-bending concepts, these mathematical theories that defy logic, are not just intellectual curiosities, they are glimpses into the profound depths of mathematics. These theories challenge our assumptions and push the boundaries of what we think we know. They remind us that even in the realm of pure logic, there is still room for wonder, mystery, and a touch of the absurd. In the 1930s, Kurt Gödel, a young mathematician, dropped a bombshell on the world of mathematics. His incompleteness theorems shook the foundations of the field. They challenged the very notion of a complete and consistent mathematical system. Imagine trying to create a list of all true statements in mathematics. You might think with enough time and effort, we could list them all. Gödel's theorems proved this to be impossible. Gödel showed that within any formal system complex enough to encompass basic arithmetic, there will always be true statements that cannot be proven within that system. Essentially, he demonstrated that there are inherent limitations to what we can prove using formal systems. The halting problem is another fascinating example of a mathematical limit. It asks a simple but profound question. Can we write a program that can determine whether any given program will eventually halt, or stop running, or loop forever? Imagine a program called halts or loops. You feed it any other program as input. If halts or loops determines the input program will eventually halt, it outputs halts. If it determines the input program will loop forever, it outputs loops. Seems straightforward, right? However, the halting problem demonstrates that such a program is impossible to create. It's a bit like trying to catch your own shadow. The very act of observing changes the outcome. The ancient Greeks were obsessed with geometry. One problem that captivated them for centuries was squaring the circle. The challenge was simple. Using only a compass and a straight edge, construct a square with the same area as a given circle. Sounds easy, right? The problem is deceptively difficult. It wasn't until the 19th century that mathematicians finally proved that squaring the circle is impossible. The proof relies on the fact that pi, the ratio of a circle's circumference to its diameter, is a transcendental number. This means it cannot be expressed as the root of any polynomial equation with integer coefficients. In the early 20th century, Bertrand Russell, a British philosopher and mathematician, discovered a paradox that, well, shook the foundations of set theory. Russell's paradox centers around the idea of sets that contain themselves. Consider the set of all sets that are not members of themselves. Let's call this set R. Now ask yourself, is R a member of itself? If R is a member of itself, then it should not be in the set of all sets that are not members of themselves because R is a member of itself. But if R is not a member of itself, then it should be in the set of all sets that are not members of themselves. This creates a contradiction, a paradox. Russell's paradox demonstrated the need for more rigorous and careful definitions in set theory to avoid such contradictions. The Banach-Tarski Paradox, proven in 1924, is one of the most counterintuitive results in mathematics. It states that a solid ball can be cut into a finite number of pieces and then reassembled into two identical copies of the original ball without stretching or distorting any of the pieces. This seems impossible. How can you double the volume of something without adding any new material? The key lies in the strange world of infinite sets and non-measurable sets. The pieces into which the ball is divided are so irregular and complex that they defy our usual notions of volume and measurement. The Banach-Tarski Paradox is a mathematical curiosity. It highlights the bizarre and often counterintuitive consequences that arise when we apply mathematical concepts to infinite sets. In 1900, David Hilbert, a prominent mathematician, presented a list of 23 unsolved problems to the International Congress of Mathematicians. These problems were meant to guide the direction of mathematical research in the 20th century. Hilbert's 10th problem asked for an algorithm to determine whether any given Diophantine equation, a polynomial equation with integer coefficients, has integer solutions. In essence, Hilbert was searching for a universal equation solver, a program that could take any Diophantine equation as input, and determine whether it had integer solutions. In 1970, Yuri Matyasevich, building on the work of others, proved that such an algorithm is impossible. This means there is no single algorithm that can solve all Diophantine equations for integer solutions. The beauty of paradox embracing the unknowable. These mind-bending math theories might seem like frustrating dead ends. However, they represent something much more profound. They highlight the beauty of paradox and the importance of embracing the unknown. Paradoxes force us to question our assumptions. They remind us that even the most logical systems have their limits. They push the boundaries of our understanding and inspire us to explore new frontiers of thought. The limits of logic rethinking the boundaries of mathematics. Gödel's incompleteness theorems, the halting problem, and other related theories reveal the inherent limitations of formal systems. They show that there will always be true statements that cannot be proven within those systems. These limitations don't invalidate mathematics or logic. Instead, they deepen our understanding of their true nature. They remind us that mathematics is not just about finding answers. It's also about asking the right questions and exploring the boundaries of what we know. The practical implications, from computer science to cosmology. These seemingly abstract mathematical theories have surprising practical implications. For example, the halting problem has profound implications for computer science. It tells us that there are fundamental limits to what computers can do. We cannot write a program that can debug all other programs or predict whether any given program will run forever. These ideas also influence fields like cryptography, artificial intelligence, and even our understanding of the universe. The search for a theory of everything in physics, for example, might be impacted by Gödel's incompleteness theorems. Conclusion: the enduring mystery of mathematics. These mind-bending math theories remind us that mathematics is not a closed book, it's an ongoing journey of exploration and discovery. They challenge us to embrace the unknown, to question our assumptions, and to marvel at the profound beauty and mystery of the mathematical universe. The paradoxes and limits we encounter are not roadblocks, but rather invitations to delve deeper into the fascinating world of mathematics.